Hello everyone, welcome back. Today we're going to look at one very interesting way of simplifying surd numerical values here. Okay, now let's take a look at how do we actually simplify this. Okay, let's get started. Right. Now, first of all, in order to simplify this, one of the strategy that I'm going to apply here would be, okay, now I'm going to make assumptions that this particular surd expression can be written in this form, okay, where my A and B would be some rational number in this case. Okay, I'm only interested to look at A and B to be rational number. All right. Now the reason why I make this assumption is because there is a surd2 inside there. So hopefully the surd would help me to simplify this correctly. Right. Let's look at the strategy itself. Now the next step that we're going to carry out will be to square both sides because our intention is to obtain a solution. Hopefully the solutions for A and B um, are some rational numbers, right? Okay, now we're going to square both sides. Okay, here. And then from here, you will notice that I'm going to swap the position here so that you can, in this case, okay, there's a square. And then we managed to get rid of the square root here. The intention of the square is to actually neutralize the square root. Okay, now there you have it. And then from here, we can expand this. So take for instance, after I expand this, I will end up with this one here. Okay, now I try to group them according to the number that does not have any surd. So here I have one group that consists of any real numbers, and then the other group that consists of a surd. Okay, by comparison, I can state that by comparison of the surd, for instance, I notice that my AB is actually equal to -1. All right, you can see that very obvious. That imply B is equal to -1 over A. So I'm going to use these substitutions to solve my A and B. Okay. Now my second equations would be by comparison to the numerical value without the surd. I have this. All right. Now you can see that. So by substitute 1 into my equations number 2, so I'm going to substitute my 1 into 2 here. Okay, let's see whether it works or not. So here I have a square. All right, now this one, if I put it in here, I should expect to get this. And then I'm going to get rid of my a square here. Now I think I need to make another definitions here. Hopefully my a and b should not be 0 then. If my a and b is 0, then that is an impossible solution here. Right? So from here, I will get a square and then plus a 2 equal to 0. All right, now I hope that's clear. Now from here onwards, okay, so I'm going to write down from equations number 3. I would have, by applying a quadratic formula, I will get myself a 1 divided by 2 here. Then that is typically a 1 or a surd2. Oops, a surd2 is a 2, sorry, a 2. And then in this case, I found that my A would be plus or minus 1, or is a plus or minus surd2. But I have defined my A and B to be some rational number, therefore I'm going to ignore this surd2. Okay. Now knowing that A is equal to plus or minus 1, Therefore, I'm going to substitute this back into equation number 1. I will get my b to be negative positive 1. Okay. And then finally, I'm going to conclude my solutions now. Therefore, I can write this as my A. So my A will be plus or minus 1. And then my B will be minus plus surd 2. All right. Now, at this point of time, you might be wondering, when I square root this, I expect to get a positive number out of this. That is our natural assumption. Okay, so we assume that this is a positive surd. Therefore, I have to do some adjustment or selection in this case, so that I'm only interested to obtain a positive result. Okay. Now, the only choice that I can have to yield a positive numerical result would be, in this case, this should be, so the selection that I'm supposed to take would be 1 minus surd 2. That's the only one that would fulfill this positive numerical result on the left hand side. Okay, just let me check for a while in case I make the wrong selection. Yep, that is the best selections that I have. Therefore, I'm going to conclude that. Therefore, this particular expression can be simplified into this form, right? Of course, you can take out your calculator and verify the result. Yeah, it's definitely true. I have already verified that with my own calculator. So I hope that this has been fun and interesting in your learning. Okay, now I'm going to show you another very interesting mathematical problem that we're going to solve shortly. All right, stay tuned. All right, here is another very interesting mathematical problems. Now, in this problem here, we are trying to solve sine theta equal to 2. Now, in order to define these problems correctly, I'm saying that the theta that we are interested to analyze here, um, is some complex numbers. Right? Now, that's the only way we can actually obtain the solutions to this equation here. If you define your data to be some real numbers, then I would say that, well, too bad, no solutions. Okay, all right. Now, if we define the data as a complex number, yes, there is a solutions to this, right? Now, we are going to revisit some of the complex number properties like De Mor's theorem. Okay, I use De Mor's theorem a lot. Okay, so let's take a look at how do we actually obtain the solutions to this. Okay, now anyway, there are lots of videos that has been uploaded in YouTube's regarding this. Okay, I just wanted to record this as a way to show you how I would actually attempt this my way here, right? But the strategy, the concept, the knowledge behind it is more or less the same, right? So I hope it'll be clear to you. Okay, now first of all, in order to solve this, knowing that data is some complex number, now therefore we have to make use of the De Mor's theorem here. Okay, now based on the De Mor's theorem, we can say that this most of the De Mor's theorem can be written in the Euler's form. So this is I sine. So that's the relationship between the Euler form of complex number and the argument form of complex number here. All right. Okay. All right. Now, if you are interested in the proof, there's another videos on that. I will put a link at the top here for your reference. Okay. And then we also notice that we can write the other Euler form for the negative or the complex conjugate as this. Okay. And then you will notice that if I add up 1 and 2 here, I would actually get EI theta. Oops, sorry. I shouldn't be using 1 plus 2 here. I should say that I'm using 1 subtract 2. Okay, so the first one subtract the second one. Therefore, I will end up with this. Okay, and then you can see that from here, I can rewrite my sine theta as 1 over 2i ei theta minus e negative I theta here. Okay, now this is our main entrance to get our solutions here. Now we know that sine theta is equal to 2, therefore we can equate this equal to a 2 here. Right? And then from here onwards, okay, it all depends on how you want to work with this. Okay, take for instance, you can actually multiply both sides by 2i if you like in this case. Okay, so therefore we have I theta minus ei theta here equal to 4i there. Okay, and then of course we can multiply both sides by exponential I theta. So here I'm going to write down this equations number 3. I'm going to take 3 multiplied by ei theta. Now that will give me a square, and then minus 1. All right. Okay, there you have it. And then we can actually solve this complex Euler form here equal to 4i using the quadratic formula, of course. Okay, now that will be um, negative 16 plus a 4 here, divided by 2. Okay, and then there you have it. Now from here, you can simplify that further. So this one can be written as, now that is a negative 12 there, which is 2 surd 3i divided by 2. 2 surd 3i. Let me see whether I got it right there. Okay, so it's negative 12. That is I there, so that is a 12. Yep, correct. Right. So from here, I can reiterate this as 2i plus or minus 2 surd 3i, or I can simply write as 2 plus or minus 2 surd 3i here. And then from here onwards, okay, from here onwards, I would be able to obtain my solution. Of course, I'm interested in the data itself. So maybe I can take a ln, for instance. Okay, let me see what do I have here. Now I can say that my I theta is equal to ln 2 plus or minus 2 surd 3 I, of course. Okay, and then at this point you might thought that we almost reached the conclusion. Okay, now most of you would actually write this down as negative I ln 2 plus or minus 2 surd 3 I, like this. Okay, just let me check for a while if I got everything correctly. Okay, just let me check for a while. That is equal to a 2. Okay, so therefore I should get, oops, I think I made a mistake here. Just let me correct that. Okay, after I divide by 2, there shouldn't be a 2 anymore here. So I just luckily I noticed this. So I'm going to mark down with a different color of my mistake here. Okay, it's cool to make mistake, no? Yeah, that's how we're going to learn. Okay, now I think this time it will be correct. Therefore, I'm going to change this also, and this one here. Okay, I'm going to change that to surd 3. Right, now this time we are good to go. Right. Now you may thought that your final answers would be this, but the structures look a bit out of the ordinary. So can we further restructure this so that it looks something more comfortable to us, okay, instead of having too many eyes there. So now let me rewrite over this side here. Okay, I'm going to use a different color here. Starting from theta equal to negative I ln 2 plus or minus surd 3 I here. Okay, I can actually write it down as negative I. Okay, by applying the logarithmics rule, so I can actually write down as ln I plus ln 2 minus, sorry, plus or minus. Okay, now that's what we have currently. And then by making use of the one of the Euler form of complex number, we know that e 2n pi plus pi over 2 I is actually equal to I, right? Now you can check that using the Morse theorem here. Okay, so the e to the power of n, I need to make a remark here where the n um, integer number. Okay, so there you have it. Okay. Now we know that this Euler form represent the complex number I here. Now the reason why I use this is because I want to reduce my um, natural log statement. So here I would end up with, oops, sorry, just let me change that. So I'll end up with my theta equal to negative I. So instead of writing ln I can actually write down this. If I substitute this and applying the logarithmic and exponentials rule here, I will end up with 2n pi plus pi over 2. Okay, now that will be the whole expressions here. Okay, now that would be um, I here. Okay, and then plus ln 2 plus or minus surd 3. Okay, now we are almost done at this point. So we try to simplify a bit. And then from here, you'll notice that I can get 2n pi plus, this become a plus, minus I ln 2 plus or minus surd 3 here. Okay, we are almost done. Okay, but there is a last thing that we can do. Just want to show it to you. This is also something that I have learned out of the unorthodox approach here. So you can see that now I'm going to write this one at the side here so that we can see what is going on. Now we know that 2 plus surd 3, 2 minus surd 3 actually yield a 1. Okay, that's a very interesting result there. So if you try to take ln both sides, okay, so therefore I can conclude that ln 2 plus this is actually equal to negative ln of this. Okay, now what does that actually mean to this term here? It means instead of writing 2 plus or minus surd 3, we can actually write this as plus or minus I. Therefore, finally, we can conclude that therefore our theta can be written as, if I try to factorize this correctly, then that will be a 4n plus a 1 pi over 2 plus or minus I ln 2 plus surd 3. Right now, that will be our final form that represent the solutions to this complex equation. Right now, I hope that has been a good learning curve for all of you, even for myself also. Okay, if you like what you are watching, don't forget to click the subscription bell and the notification bell so that you can get the latest video. Until I see you guys again, take care, everyone.